So welcome everybody to today's seminar. Today's speaker is Takaaki Aoki, and he will talk about the potential landscape of human flow in cities. Please take it away.
Thank you. Thank you for introduction. So I'm very happy to talk in this seminar series. So today I'm talking about the potential of the human flows. So firstly, I'd like to maybe change. Okay, I'd like to introduce myself. So I got a PhD in physics. So I'm not a mathematician. So please, please communicate with the disciplines. So I was firstly worked on computational neuroscience. So to be honest, I was trained in physics, but at the almost big at the beginning, I applied the knowledge in the physics to the other field of science. So after that, I go back to the physics, and in particular on statistical physics and the topic of nonlinear dynamics, such as the coupled dynamical systems. So after that, I moved to the research field to network science. So maybe it is more closer to the applied mathematics. And in that case, so now I'm more working on other topics. I'm working on for example, the city and load as a pattern formation of nonlinear dynamical system. And then nowadays, I also working on the human flow data set. Today, I talking on this topic. So, okay, this one's. So I try to explain the background first. So nowadays, the human flow is a available data set, and it gives a very vital information on the library, human behavior, and cities. So this picture shows human flow in Tokyo metropolitan area at the morning and the evening. So people are moving from one location to another in daily lives, and this is related to the human decision making, where people live, work, and going shopping and other works. So from this data set, we would like to know about the actual shape of cities. This is the motivation of this study, in particular in the field of urban studies. This is a scientific field. So in this study, I want to focus on this question. So where is the attractive place of people movement, not just populated place? This is related to the basic question in the urban study, that is, where is the city center in the cities? So we want to know about the shape of the city, in particular about the central location of cities. And we want to also know about the base of the attract places. So this is related to the question, where is the limit of cities? But in this today's talk, I focus on the first ones. Yeah. Move to the next slide. So the idea is very simple. We want to, I extract the potential of human flows. So this is because that the mobility data is aggregated as a OD matrix. This is an origin destination matrix. So this is the relational data between the places, and it can be seen as recognized as a network data embedded in the spaces. So this data is very massive like this. This is a Tokyo area, and I show the links from the origin to the destinations on the daily trips. So you can see this is very messy and not easy to see some of the structure of this stage is urban area. So the idea to solve this problem is that we extract potential from this OD matrix. So after getting such a potential, we can visualize on the maps like this. So it gives a very intuitive perspective of the urban structure. So this is the goal of these studies. So before that, next slide. Before that, I would like to look back to the literatures. So the researchers have tried to introduce concept of the potential in the urban studies. They are based on the Helmholtz theory. So the scalar vector field can be decomposed into a gradient of scalar potential and vector potentials. So the firstly, locational potential or attractiveness are introduced in this scientific field. It go back to about half of centuries. And later, some theoretic, some models use a concept of the potential. And very recently, people working on the real data and empirically calculate the potential of the mobility data set. So if you have a question, please interrupt me. It's okay. And so I'd like to introduce some of these literatures. The first one is a locational potential of gravity model. So this picture shows a potential of the populations by Stewart. So you can see that here is a higher potential area, and it's gradually decreased to the west coast. So it's based on the gravity model. So gravity is coming from the idea of physics, but it's known as a well-known model of the human flow. It's an idea coming from the physics, but it's applied to the urban structures, urban studies. So it just shows this values. It's L is a number of the people living in the locations, and these distance from the locations. So this is very maybe interesting, but this measure is not obtained the mobility data. It just shows distribution of the peoples. So, and there is another and critical suspicions what this potential means in the urban studies. It's interesting, but for example, this value, what this value means. So this is very critical questions about the potentials. There are several researches about the potential, but they are always subjected to these questions. So I showed another researchers. So this is a very recent studies, and they get the OD matrix from the mobility data, but this is a matrix. So this process try to convert to the matrix data to the vector field data by averaging all trips. So this picture shows the procedure. So from this location, people moving to the another locations. For example, some of people moving to here, there are many of people moving here. So instead of this matrix data, so this authors averaged this movement and only considers mass of the movement of this let allows. So after that, they show that the resultant vector field almost looks like relational. So they argue that they can introduce some potential, a scalar potential field. So this is a result in the case of the Tokyo area. It looks like they're very interesting, but unfortunately, there are several shortages. First, Tokyo area, known as a polycentric city, it has several sub-centers, but you can see that it has only single peaks, this monocentric. And it peaked at the Shinjuku area. It's a very populated place, but it's known as a sub-center. It's not a main center. So the central place is somewhat wrong at the wrong places. And another question is very serious because the potential has spread over the non-land area, for example, spread over the sea. So what's the potential mean at the oceans? So our contribution to this topic is that introduce potential based on the combinatorial Hodge theories. So previous works based on the harmonic Hodge theories, but unlike the electromagnetic field, the human flow not describe the electric field, but as OD matrix. So the question is that the technical question to be solved that how to introduce a potential to the matrix. So we use the technique in combinatorial Hodge theory. We use a unique decomposition graph flows. So this illustrates this idea. So given the now flow of the people on the graph, so this graph flows uniquely decompose into the one of the gradient flow of the potential, and the second is the harmonic growth, and the third is the curve flows. So in particular, we focus on this component. So the blue-colored number shows potentials, and flows between the nodes can be given by this difference between the potential. So next, I would like to overview this method. So I based on the paper and mathematical published in mathematical programming. So in this paper, the authors defined a combinatorial version of the gradient curve divergence on the indirect graph, and each edge has flows. And so you can see that the gradient is given by just the difference between the potentials. And the curve is like this, and divergence of the sum of the incoming flows. And based on these definitions, the authors argue that there's a flow matrix of space that can be orthogonally decomposed into these three different subspaces. So using these properties, so we applied this idea to the human flows data sets. So I will go back to the previous one. So the edge flow is a skew symmetric. So it is necessary assumptions. So, but the OD matrix is not always skew symmetric. So we considered the naflows like this. And then this Y matrix became a skew symmetric. And we defined the potential of S Y as a solution of the following optimization problem. So gradient of the flows should be different. Y is a given data, and the S is a potential. S should be minimized these values. So this is equivalent to the R2 projections of the Y onto the space of the gradient flows. So we can solve this minimization optimization problem by projections. So with some proper Euclidean some inner product. So we just consider the simple Euclidean inner product, and then we can define the normal equation like this. And this delta is a graph Laplacian. And from this equation, we just get the potential like this, getting the most inverse, most Penrose inverse. So,
Takaaki, sorry, I have
yeah.
a question. This
Yes, of
space
course.
Y, the curly Y, is that the space of the gradient flows?
Y is the space of the skew symmetric matrix.
Ah, okay. Ah, yeah, true. Sorry, it's yeah, space of the full matrix. Okay, sorry.
Yeah.
Thank you.
Yeah. And this space is unique, orthogonally decomposed into the image of a gradient and the image of the adjoint operator of the cow and others. Yes. So by this definition, the sinks is a location with a higher potential. Usually in a potential in a gravity is a lower is an attractive point, but by this definition, it's a higher potential gives the sinks. Okay, it's also called the negative potential, but this is just a sign of this value. So, and this is a network embedded in spaces. So the distance is the location distance. Distance between location is very important factor. So it determines edge of the graph. So we find that the net movement matrix has many zero elements in the case of the real data set. So there are the two cases of zero flows. So in general, trip became rare for long distance. It's very natural. So for these cases, we did not assign edges between the locations. But there's no trips even if there are short distance. So in that case, we assign the net flow is zero. So using this representation, we can take two options for the zero element. One is no assigned no edges. One is the edge flow is zero. Okay. So in the practical cases, we assume the pair of locations connected if the low distance within some threshold. The threshold is chosen to be include 99% of all trips. So we want to cover almost all trips in our real data set. So, and we also mention about the simple cases, that is a complete graph case. That it means all pair of locations connected. So in this cases, so we can solve this equation more simplified, and it gives us this divergence. So it means that the potential became just difference between the incoming flux and the outgoing flux. So in this sense, so I think that we think that this potential gives a very interpretable meaning. So it was a problem that what the potential means in urban studies, but in these definitions, but potential gives a very interpretable meaning. So, okay, I would like to move to the seminar real example. So before moving to the real example, so any questions? It's okay. So I'll show the seminar examples. So firstly, I'd like to show the case of London. So this picture shows a potential landscape in a greater London using homework trip dataset. So you can see that there's a largest peak at here. This point is a city of London is 001. It's namely the center of London. And you can see that another center here. It's a second highest peak here. It's a Tower Hamlet 033. These locations include Canary Wharf. So this is the leading financial center in the UK. And you can see that the other area has a lower potential like here. It's a residential area and serving a source of a commuter to the sources, to the centers. And this data set has information of the which transportation method people use. So by selecting the flow by the specific transportation method, we can see another picture of London. The left panel shows a potential landscape only by the public transportation methods, such as metro and public bus. And the right panel shows a potential by the private cars. So you can see that the best public transportation given almost a similar picture on the previous ones, but private car is somewhat different. So you can see that it's almost a very single peak. For the case of public transportation method, there are several sub peaks, but in the case of the private car, such a small sub peaks disappears, and only the largest peak remains. So in the urban studies, so there's a distinct urban structure that is one is a city center cities, the other is a multi-center city. They are completely different in the literature of the urban studies. So based on the transportation method, London has another picture of the cities. Another picture is mean single center cities.
So before you go to Tokyo, in that picture of London, do you know what the area on the complete left is? There's like a big area which is quite green.
This one?
Yes.
I forget that this is a very it's a suburb area. So it's mainly people move to the city center, but nowadays large metropolitan area has sub peaks in the suburb areas. This is one of such kind of suburb areas. I forget the name of the locations. So sorry, but
no worries.
Yeah.
Right. Thank you.
Yeah. So I also applied this method to the Tokyo metropolitan area and using the homework trip data set. So you can see that this picture. So this is the largest peak at here. Here is the Chiyoda city, and this is the empirical palace and its surrounding area. This is the top of potential, and this Chiyoda city hosts it's a center of the not just Tokyo. It's a center of Japan. It has many political institutions and financial center and many headquarters, and also Tokyo Central Railway stations. So, and there is another sub peaks in the Kawasaki area and the Yokohama area, Chiba area, and also in Hachioji area. It's here is Atsugi area. It's not U.S. not the Navy, U.S. Army bases. Yeah. So the Tokyo dataset has a very long trajectory and a time evolution. We can see the time evolution Tokyo area from this dataset. So you can see that over the 30 years, Chiyoda is the top of the potential. And also we found that Chiyoda and Minato, Chuo, Shinjuku, and Shibuya area is occupied the top 5 ranking by by potential over the years. And but this is a unchanged area, but from this time to here, so new peak appeared here. Here is a Tachikawa area, and after that, the Omiya area became centers. So this place is known as the business square that is envisions the national development plans. So these plans aimed to merge nucleated urban structure to solve the over-concentration at the central place of Tokyo. So, and in the urban studies, there are some argument about emergence of edge cities. So the large metropolitan area have some edge cities. So this is a finding of such kind of emergence of edge cities. So I skip this one. So I move to the next topic, to the how to identify the city centers. So in the classical view, city has only single centers. But nowadays, city has become more polycentric along with the change of transportation method and other factors. And this is very ongoing phenomena, because after the COVID-19, there's many increase of the number of the remote workers. So it drastically changes the structure of the urban metropolitan areas. So people want to know about how the city are changing. So there's several methods as proposals to identify city center in a data-driven manner. So we want to propose another method to identify city center based on the potential. So that is a significant thing of the multiple aim in the Tokyo. So okay, back to this point. So the idea is that there's two important points in this method. The one is the significance. So there's some peaks in a potential landscape, but some peaks is not significant. Some people will be significant. We want to identify only the significant things compared with the null models. So we defined the null model. We adapted the link shuffling null model among the randomized reference model networks. So this null model randomly shuffle association between the edges and the networks, and it flips the sign of the frauds. So using this model, we can obtain sample distribution by the Monte Carlo sampling, and we can perform multiple comparison tests with a standard procedure. Then we can detect the significant things. And the second point is the diversities. So in the urban studies, the city center is not just a highly concentrated places, highly populated places, but a place of the diverse type of activity. It's based on the Jacobs. So very fortunately, our data set has information on the trip aims. So we divide it into the data set in two types. So one is the commuting trips, and the other is shopping trips. So we are based on these two types of the trip aims. So for each flows, we identify significant things and significant sources. So then we can categorize three metrics. So this type is a compound thing. So it means that this location is a significant things for commuting flows and also for the shopping flows. So in our cases, this is a true city center. So this is the result in the Tokyo metropolitan area. So the red colored area is a compound sinks. So these points attract the commuters and shoppers. So you can see that Chiyoda area still are compound sinks, and there is another compound sinks in Chiba and Kawasaki and Tachikawa area and other well-known populated areas. And I focus on the central places. So here is the Chiyoda. And you can see the Tokyo Bay Area is not the compound thing, just a commuting thing. It attracts commuters, but not shoppers, because they're a very industrial area. So this is very attractive area for commuters, but not for the shoppers. So you can see that here is a location of the Tokyo Disney Resort. It's a sink of the shoppers. It's very natural. So we want to validate these detected centers, but very unfortunately, there's no ground truth for comparisons. So alternatively, so we consider business scores that were defined by natural plants. So, but there is several issues for comparison because that the core is just a political plant, just a plant. So there's no guarantee to be actual centers. And another point is some area may be developed unrelated to these plants. And the final point is that this business score is as a very too wide compared with the actual center. So we just checked that it includes this business score includes the detected center or not. So this is the result. So the colored area shows the business scores. So here is the Tokyo area, Tokyo Central area, and here is Yokohama business score, for example. And you can see the green circles and the green triangles. And green circle is a centroid of detected compound sinks. And the green triangle is a centroid of detected commuting sinks. You can see that green circles, most of the green circles included are located within the sum of the business scores, except this here, Yokosuka area. So you maybe know that Yokosuka is the place of the US Navy bases. So it was developed unrelated to Japanese national development plans. And we found that some business score has no sinks. It means that they are planned, but finished just planned. So I'll go to the final topic. So I want to know about how much percentage of human flow can be represented this potential. So I evaluate the percentage of the gradient component. This is the R squared value in the statistics. So I evaluate this R squared for the data set core-based statistical area in USA. So very fortunately, USA gives a definition of the area of the cities. Unfortunately, other country doesn't have such kind of the definition, but very fortunately, USA has such kind of a definition of the cities. So we applied this method into each of the city in the USA and evaluated how much percentage of the human flows can be represented as a gradient component. And you can see that this percentage widely varies among the areas. And the lowest one is here is New York area. Highest one is about almost 100%. in some area in here in the west, maybe here or here. And also Las Vegas has a very higher percentage. So we found that the smaller city tend to be higher percentages like this. It's based on the populations, the percentage decreasing. So I skipped these ones. So almost 40 minutes. So let me summarize my presentations. We identified the potential of the human flow directly from the press-to-press interactions using the unique decomposition method in the combinatorial Hodge theory. And it gives a very intuitive perspective of the human flow, and this provides a very easy to use visualization tool in human flow. And I implemented this method in our package. And I think that for future work, this method is also applicable to as a data set, such kind of internal migrations or IO table. It's money flow between the economic sectors, or job change flow between the sectors, or big technical companies, for example. So this is references. So using the last few minutes, I'd like to ask the audience. So I'm working on the potential, but I want to go beyond the potentials. So in our studies, so the hierarchy of the city is a very important concept. So I want to extract the hierarchy of cities from the flow data set that will be related to this kind of the optimization problem. So I mean, so in the previous sense, so I give the undirected graphs, but I want to know about is it possible to find optimal tree graph? So not just optimize the potential S, but also optimize the tree structures. This is a subgraph of the tree subgraph given connections of the locations. Okay, this is last slide. So thank you for your attention.
All right, thank you, Takaaki, very much for the talk. Before we go to the question, please, everybody, unmute yourselves and let's thank the speaker by an applause.
Thank you very much.
All right, it's time for questions. Okay, then I will start with questions.
Yeah.
I was wondering, how do you get your data? Because you're saying you are working with real world data, right?
Yeah. So for example, I would like to mention in our London cases. Okay, this is the public data. So the UK National Statistical Agency gives a data set in the public data as a public data set. So this is the kind of a census data. So you can get the data from the website of the UK National Agency of the UK. This Tokyo data set is almost another census data in Japan. So sorry, this one. So the person trip data set is very easy to get. But unfortunately, so nowadays people are studying on the GPS-based data set. So this is because of privacy issues. So it's not easy to obtain. So but in Japanese cases, so some telephone companies sell such kind of data by anomalizing their data set. So, but it's very expensive and it's not easy to get. So I think there USA also there are several data serving companies, and they are selling some of the data sets.
Mm. And do you know how do they distinguish between like commuting and shopping? I mean, if they know that I went in the morning from place A to place B, how do they know, what purpose was my trip?
Yeah. So the person trip data set is a survey data set. So this is ask the people, why did you went to some place to another, and what's the transportation method you used? So this is very costly surveys. So in the Tokyo cases, it collects maybe over the million people answered this survey. So very, 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 very expensive surveys. So that's the reason Japanese government only do this survey every 10 years.
So there are no data, because I was wondering exactly on this, like, given your results, can you analyze the data before, during, and after COVID, and see if there are some significant changes? But I guess the data is not there if it's so costly to gather it.
Yes, so unfortunately, this person trip data survey data set are recently done just before the COVID-19. So I want to know about how the urban structure changed before and after COVID-19, and many researchers are discussing about this point based on some of the GPS tracked data set. So very fortunately, last month I bought the data set, and I'm working on such kind of data set.
Really?
Yeah.
We invited you too early then. We should have waited. How long does it actually take you to process the data?
Yeah, it's very easy. So maybe so I already implemented this method in our package. So even an urban graduate student can use this method if you have the data set. So within a couple of days, so I can do the seminar work. So yeah.
Okay. Yeah, that's great. Maybe I will let some other people ask their questions.
I wanted to ask a question. So you had this question at the end, can you approximate the flow using a tree?
Yeah.
I was curious, is there any chance that this is like an optimization problem with a greedy solution? So for example, when you look for minimal spanning trees, you have a weighted graph. The greedy solution is optimal. Is this known that the greedy solution is not optimal?
I think this is several heuristic methods to obtain such kind of the tree. So I think the minimum spanning tree is one of the solutions, but I'm just wondering about this is a unique or truly optimal solutions. So very fortunately, so based on the this paper, we can argue about the obtained potential is a unique solutions, and the optimal solution of this method, this program. But there's there's several variations in researchers, for example, like this. they has argued that this is a potential of the dataset, for dataset, or also the hierarchy of cities. So there's some heuristics method to obtain such kind of hierarchies, but they are not guaranteed some mathematical basis. So I'm wondering that is it possible to define such kind of the desirable subspace in possible tree subgraphs? So of course, so you know that this set of the tree subgraph is very anomalous, very extremely large. So it is not easy to find the minimum solution, truly minimum solution. So that is a wondering point I want to ask. Yeah.
That makes sense. Yeah, it's a nice question.
Are there any other questions?
So this is something I haven't seen in a long time, but it may be relevant for this. But from graph theory, there's this idea of trophic analysis, and I can't quite remember whether the intent is to solve this or something similar. I'll also note, kind of along the lines of the trophic analysis, as you had mentioned, the in and out tables, and I know some economists have, or financial mathematicians, I can't remember which, took a look at trophic analysis for doing this sort of thing for in and out tables. I can't remember the authors.
Yeah, thank you very much. So if you find some references, so please send me later. So sorry, I'm not sure about the tropical analysis. So if you have some references, please send me later. Is it possible?
Okay, I will.
Of course, if you find so.
So Robert McKay is I think was the primary author, but I'll send you the.
Okay, I'll check. Thank you very much.
Are there any other questions or comments or answers? Okay, if that's not the case, then thank you again for the wonderful talk, and I'll stop the recording.
Thank you very much.